Hello everyone, I welcome all of you to this lecture. In previous lecture, we have started with basics of compensators. We have discussed types of controllers like discrete and continuous. Then we have seen proportional controller in detail. After that, we have seen basics of integral controller. Now let us discuss about derivative control action as well. Okay, so in a derivative control mode, the controller output is proportional to the derivative of the error. Okay, so the output can be expressed as P is equal to KD into DEP divided by DT. Okay. So if you see here, derivative mode controller action based upon the rate of error. If you see, this is error and this is the controller output. Okay. Now if you see this error, this is with respect to time. Okay, so this is the positive side of error and this is the negative side of error, and there is a controller output which is given over here. Okay, now if you see here, see the change. Suppose the error is changing like this continuously, then your error will the controller output or derivative control output will be what? Stable. Okay, again if there is a change in slope, means of slope is now this is the increasing slope, and with respect to this slope is somewhat decreasing. So here we will get the output like this. Again for some steady state we will get the output like this, and for the decreasing slope we will get the output like this. Please see carefully the deviation that we are getting. See where there is a decreasing slope, how much output is changing. See for this continuous increasing slope, how much output we are getting. See these amplitudes carefully. Okay, and conclude the output of a derivative, how it is changing. If it is steady, it is giving output like this. Okay, so this is some this 50 is showing some offset values. Okay, and when there is a decreasing slope, it will give below 50, this base level. Okay, so this you have to observe, and that is P is equal to KD into derivative of EP divided by DT. Okay, so let us discuss about the characteristics of derivative control action. If error is a 0 or the error is constant in a time, the mode provides no output. See, this is very important. If error is 0 or error is constant in time, the mode provides no output. Okay, see here the error is constant. Okay, so that's why here you are getting a baseline, not increase, not decrease. Okay, so that is discussed over here. If there is an error, for every 1% per second rate of a change of error, the mode contributes an output of a KD%. So whatever the KD is given in this equation, that much percent it will add error. For direct action, a positive rate of a change of error produces a positive derivative mode output. This is very important. What are the advantages of a derivative controller? Now we have to discuss. It can overcome the overshoot and saver cycling. When there is overshoot, then we have seen that for that overshoot as well, it is not abruptly changing. So it can overcome the overshoot and saver cycling. Then it has a rapid response to counter the effect of rapid changing errors. Okay, so to counter the effect of that rapid changing response or errors, we can say it is helping so much. It responds to the changes of the speed and direction to the deviation. It does not affect the steady state error directly, but anticipates the error. Okay, that is very important. It increases the stability of the system by initiating an early corrective action. Okay, so if you see over here, this picture is giving you much idea about the derivative action. So that's why in previous lecture as well I have told you that please see the online simulators of a derivative, integral and proportional. I think proportional is very simple. Just understanding, just apply the different waves to integral and derivative controller. There may be online simulators, and just observe how output is changing. Apply continuous increasing slope, apply continuous decreasing slope to both derivative and integral function or that block, and just observe the waveforms, or you may get ready-made video of that as well. Okay, that will give you a much idea about the action that is provided by this derivative or integral controller. Okay, now again there are some disadvantages of derivative controller. It cannot be used alone again, since it cannot give any output for zero or constant error. Okay, for zero or constant error it is not affecting, that we have seen here in this point. It does not affect the steady state error directly, so that's why it is not used, because it cannot give any output for zero or constant error. It is ineffective for slowly changing error and hence causes the drift. For slowly changing error it is ineffective. It amplifies the noise signal and causes a saturation effect of the system. It again amplifying noise signal, and it does not eliminate the steady state error or offset that we have seen earlier. Okay, so these are the disadvantages of a derivative controller. Okay, now I think you have the basic idea about advantages of a proportional, advantages of integral and advantages of a derivative, and you will give it will give you the basic idea about the combination of that as well. Means if you combine this PI, you will understand what will be the advantage of that. If you combine PD, then you will understand the advantage of that PD as well. Okay, so that part now we have to study. So now we have to study that proportional integral controller. Okay, but before that, again I am telling you that please see the advantages and disadvantages of each controller: proportional, integral and derivative. So I have given you a basic idea about that, and that will give you a much idea about the PI, PD, PID controllers. Okay, now let us discuss the combination of a proportional and integral controller and how the output that we are getting in such a systems that we have to see now. The PI controller combines the behavior of the integral controller and proportional controller. Okay, so this allows the advantage of both controller types to be combined: fast reaction and compensation of the remaining system deviation. Okay, so this is the outcome of this PI, that is fast reaction as well as compensation of the remaining system deviation. So for this reason, the PI controller can be used for large number of controlled systems. Now such a controllers which are combined are mostly used in systems, okay, or industries we can say. In addition to proportional gain, the PI controller has a further characteristics value that indicates the behavior of the integral component as well. The reset time, that is nothing but integral action time. Okay, so let us see more about this. So if you see, this is my controller, which is PI controller, and suppose the system deviation xt is like a step signal, then you will get the manipulated variable like this. Okay, now recall the proportional as well as integrals separate response. In case of a proportional only, you will get a response like this, something like this, and in case of an integral you will get a response starting from this 0. So it will increase like this, that slope will increase from 0 like this. But now we are combining this, so that's why this is not starting at 0, it is starting at this point. Okay, and we can say that this is the reset time. Okay, so if you see here, from this point it is increasing. So whatever the reset time that we are getting here, that is a TR. Okay, so that's why it is written over here, that is in addition to the proportional gain, the PI controller has a further characteristics value that indicates the behavior of the I component, that is the reset time. integral plus action time. Okay. Okay, so again you can clearly observe here it is not starting from 0, it is starting from this point. So this dotted line is shown over here, and TR is a reset time. Okay. Now again if you see the equation, again it is very simple because you have studied proportional and integral, just we have to add that. This control mode results from a combination of proportional mode and the integral mode, and the output can be expressed as PT is equal to Kp EP plus Kp Ki integration of EP dt plus Pi 0. So where Pi 0 is equal to integral term value at t is equal to 0, that is the initial value. Okay. Now in terms of a system or control system, this diagram will be like this. So here the reference input will be there RT, and from CT we are taking a feedback, and this is a BT over here. Okay. The error ET will be RT minus BT if the feedback is negative, and it will be RT plus BT if feedback is positive. When we add Kp proportional constant, this block will look like this, and parallelly we are adding integral function as well. Okay. And as these blocks are connected in a parallel manner, so at this end these integral and proportional, we can say, parameters must be added over here with the help of summing points, and after that whatever the CT, the actuating signal that you are getting, that is given by CPI. P stands for proportional, I stands for integral with respect to time. So all other things that are shown over here, these are the with respect to time. So here the output of this integral will be Ki integration of ET dt, and output of a proportional block will be Kp ET, and it is added again. Okay, so that's why here the Kpi t is equal to Kp ET plus Ki integration of ET dt. Okay, so this is the broad equation of this proportional integral or proportional plus integral control. Now if you see this equation and if you convert this into transfer function, or if you convert this into, we can say, S domain, you will get something like this. Just take the use the formulas and convert. It is directly written over here, so you can do your mathematics and you can cross check the answer. So CPIS divided by ES will become now Kp plus Ki 1 upon S. Okay, so here this 1 upon S is for this integration. Okay, if it is derivative, it will be multiplied by S. Okay, so that you have to understand. So here for this, if you take let me explain this. Okay, so it will be very easy to understand. If you take ET as a common, okay, if you take integration and if you take this ET as common and if you take it to this side, and if you convert into S domain, this Kp will be like this, Kp plus this Ki will be Ki, and this integration symbol will be converted into, we can say, 1 upon S. Okay, so this integration is replaced by 1 upon S into S domain. Okay, now let us discuss how combined effect that we are getting. Okay, and as well as you will get the overview of separate functions in this diagram. Okay, again see the error is shown over here. One thing I want to tell you that this error is taken like this. Okay, so error can be anything. It can be like a sine wave, it can be continuously increasing, it can be continuously decreasing, or anything. For just explanation purpose, I have taken the error like this. This you have to keep in mind. Error is not fixed. As it is error, it is not fixed. That you have to keep in mind. But for understanding purpose, I have taken this diagram. So here the proportional integral action showing the reset action of the integral contribution that you have to see here. So this is the error again, and if you see, this is the time domain, this is the plus, this is the minus part of the error. Okay, and here this is the controller output, and see if you see the combined effect of this or combined output, it will be like this. It is shown as a composite. Okay, composite, or we can say combined effect of proportional and integral. So for this type of error, the system's deviation will be something like this, or the control action will be something like this. Okay, and if you take unitedly proportional only, or only proportional response of a control action, then it will be like this, like dotted, which is shown over here. And if you take only integral, it will come like this, but it is combination of a PI, so it will be composite. So actual output that you are getting in PI is like this, but for understanding purpose, the dotted lines are also shown, how the proportional will behave and how integral will behave. Okay, now I think you got the idea about this. Now let us discuss the characteristics of a PI controller. Okay, when error is 0, the controller output is fixed at PI 0. So when error is 0, the controller output is fixed at 0. If there is an error, the proportional term contributes a correction. See this, proportional term will contributes a correction, and the integral term begins to increase or decrease the accumulated value depending on the sign of the error, and the direct or reverse action will be done. Okay, so this diagram is sufficient to explain all these points. Okay, again, if you see here, this is controller output, and whatever that you are getting over here, that is a time domain. Okay, so characteristics of a PI controller. So when error is 0, that PI is 0, that we have seen, and the proportional term contributes correction, and integral will increase or decrease based upon the accumulated value. Okay, so these are the some characteristics of a PI controller. So how the PI controllers are useful? It provides better stability to the system. Okay, it provides simplicity and directness. It fully eliminates the steady state error, that is very important. Okay, it has good transient response, and it stabilizes controller again. So if you see this diagram, collectively we are getting the advantages of proportional and integral, so that's why we are getting some advantages like this. Okay, and characteristics also we have seen. Okay, so let's move towards the next point. Now the next point is PID controller. Now this is the, we can say, most flexible and we can say most useful controller, which is giving you the advantage of proportional, integral and derivative at the same time. Okay, but the design will be somewhat complex due to that we can say addition of the three types of systems. So in addition to the properties of a PI controller, the PID controller is complemented by the D component. Whatever the disadvantages in the PI will be what we can say removed by this PID controller. Okay, so I think we have not seen the disadvantages, just see first disadvantages and then we will move towards the PID. So it takes the longer time to stabilize the controller gain than proportional controller action. So it is taking some longer time. Why longer time? Because integration is added. I think you got the point, that point. It suffers from only oscillations induced by the integral overshoot. Okay, so again the oscillation problem due to this integration. It requires excessive stabilization when the process has many energy elements or a dead time. Suppose there are some energy elements, then it requires excessive stabilization. You know, I think different types of energy elements like capacitor, inductor and all other things. Okay, so for that you will require the excessive stabilization. So these disadvantages are removed by the derivative component. So that's why we have to study this PID. This takes the rate of change of the system deviation into account. It is taking the rate of change of system deviation, that is again important. If the system deviation is large, see, if the system deviation is large, the D component ensures a momentary extremely high changes in the manipulated variable, while the influence of the D component falls off immediately. The influence of the I component increases slowly. Okay, so where there is influence of a D component or derivative component, then I will not work or integral will not work, and whenever the influence of integral component comes into picture, derivative will not work. So they are complementing each other. So that's why these are the very useful controllers, PID. And if the change in the system deviation is slight, the behavior of the D component is negligible. Okay, so whatever the system's characteristics that we have seen right now, the conclusion is that suppose at some point integral is working, then derivative is somewhat giving a, we can say, negligible response, and whenever the derivative is working, integral will give you some we can say negligible response, because at that some characteristics of that we can say system deviation, only the active part will give you the output, and that is, we can say that we are getting the output. For some period of time, derivative will work very we can say very great manner due to the derivative components and that characteristics of deviation, and for some part of a period of a time, we can say, or to that deviation, integral part will come into account. So that's why while influencing the D component falls off immediately, the influence of I component increases slowly. Okay, so that is given over here, and I think you know the integral and derivative are complementing each other. Okay, so there is a difference in between integration and derivative. I think you know this. This behavior has the advantage of a faster response and a quicker compensation of a system deviation in the event of a changes or disturbance variables. Okay, and the disadvantage is that the control loop is much more prone to oscillations, and that is setting is therefore more difficult. Okay, so this disadvantage is there, one disadvantage is there, but most of the advantages are there. If you combine advantage of PID, you will get over in PID. Means if you take one advantage of P controller, one advantage of I controller, one advantage of D controller, all these three advantages you will get in this PID controllers, but some oscillatory response problem is there. The disadvantage is that the control loop is much more prone to oscillations, and that control loop is we can say making a problem, we can say, and that setting is that's why difficult, but the output that you are getting is we can say desirable. Okay, so this is all about the PID controllers basics idea. So let us see in terms of this graph. So now see here, this is the system deviation. Again, the system deviation is shown in terms of step input. This is the controller, which is PID. Input is applied and the output is manipulated variable Y. Now see here, you are getting a response something like this. So you will get the reset time like this, delay time like this, derivative action time like this. Okay, so these are some characteristics of the graph, but actually you will get the graph like this, which is a combination of three characteristics. One is proportional, another is integral, and third is a derivative. Okay, so I think you got the idea behind this. So again, in terms of mathematics, this is one of the most powerful but complex controller mode operation, combines the proportional, integral and derivative modes as discussed earlier, and the output of this mode can be expressed as just a combination of three equations. P is equal to Kp EP for proportional plus Kp into Ki into integration of EP dt for integral part, plus Kp into Kd into dep divided by dt plus some, we can say, offset value, okay, like Pi0 or P out we can say. So here again, if you see the diagram, if you differentiate the diagram of the integral and proportional, one more block is added over here. I think this is very easy to understand if you know the basics. Okay, so again the reference input is RT, BT is feedback element, and this et is applied at applied to derivative, integral and proportional at the same time, and whatever the output of derivative control is given over here, that is kd into d et divided by dt. Output of a proportional will be kp into et, and output of a integral will be ki integration of et into dt. And at the output we have to add this mathematically, so summing point is added over here, and we are getting cpi dt, in which p for proportional, I for integral and d for derivative, and that is given to plant, and the output that we are getting is ct. So much excellent control action is happened in this, so that's why this is much powerful controller PID, and due to this powerful actions of integration, proportion and integral at the same time, it is more complex, that you have to keep in mind. Okay, so where you require most the accuracy is most important point, we can say, and systems functionalities, you want that better systems functionality, at that time you have to use PID controller over. Okay, so this is the important thing. So here again the equation is given over here. If you see the this equation into S domain, then it will be like this: CPID S divided by ES is equal to Kp plus Ki into 1 upon S plus KdS. Okay, so this Kp, if you take this integration, if you take integration and derivative, and if you take Et common, and if you take Et over here, it will go in denominator, and it will, if you take S domain, then this CPIT will be CPIDT will be CPIDS, and ET will be ES, is equal to this Kp for proportional, this Ki for integral, integration symbol converts into 1 upon S, and this derivative of this d by dt will be converted into S. Okay, so these are the basic formulas which can be used. I have written over here directly, so you have to just use the mathematical rules and you have to solve this. So you will get like this. This is very simple to solve. Okay, so you will get the transfer function like this. Now it is very interesting to see the 3-mode controller actions which exhibits proportional, integral and derivative action. So again I have taken error of like this fashion. So this is my error, so this is my time, and we are getting error like this. Now whatever the composite signal that we are getting, that is like this. This is the composite or combined signal, means it is combination of derivative, integral and proportional. And if you want to observe the derivative, proportional and integral separates action for this particular type of error, then the derivative will be like this. You are getting here, it is shown over here, the derivative will like this. Okay, so this is not like this derivative, this is composite again, because you may confuse over here due to this unclarity. Okay, so this is the derivative, then the integral will be like this. Okay, from this it will start like this, the proportional will be something like this. Okay, and the combined is shown over here. This is your composite or combined effect of a PID. Okay, so this is all about the PID controller and its action. See these diagrams carefully, whatever we have seen related to proportional, integral and derivative. Okay, now the time analogy of PID controller, this is very interesting to understand or to keep in your mind. So if you see the proportional, it is taking care of a present time only. Okay, so only consider current position, whatever the signal will be there, that will be multiplied by gain directly. So not aware of the current direction and error history. So the proportional controller don't care about the current direction or error or history, it is just considering the current position only, and that is multiplied by the gain. But if you see the integral, it is taking care of a past time, only compiles an error sum of the past, not aware of the current distance of a signal from set point and the current direction. Okay, so this is the integral fashion. And if you take a derivative, it will take care of a future time, so only considers current direction or a trend, now aware of a current distance of a signal from set point and of a error history. So if some system is taking care of a present, past and future time, then we can say that it is a best system, because if it is taking care of present, past and future, then it is taking care at all time, we can say. So this is the time analogy to consider PI control for most of the applications. Okay, so this is the time analogy. Again, if you see this diagram, this is a very interesting diagram. Okay, so in which one, we can say, controller output is taken over here. This is output without control. It is not having any control, if you see this output, and the same output with proportional action, integral action, proportional plus integral action, proportional plus derivative action, proportional plus integral plus derivative action is shown over here. Okay, so if you see, this is your set point, and this is the control variable, this is position deviation, and this is the positive deviation, and this is the negative deviation with respect to time. Then see these different numbers, and it is given over here. Then you will understand actual way of its control. Okay, so for example, suppose if the output without control will be like this, and if you are using proportional controller, then it will be something like this, dotted. Okay, so the numbers are given over here. So this is just given for your understanding only. Okay, so just, it is very interesting. Just take your time and see this, and you can also note down on your in your notebook, okay, for better understanding. Okay, so let us see the advantages of a PID controller. It reduces the overshoot, which often occurs when integral action is added to the proportional control action. Why it reduces the overshoot? Because derivative action is over there. Okay, so it counterattacks the lag characteristics introduced by the integral control action. Then it approaches the tendencies towards the oscillations. It senses the rate of movement away from the set point and gives corrective action earlier than only with P or PI. Okay, and if you see the advantages, again, it is more effective for control process with many energy storage element than PI, and it eliminates the offset, that is steady state error introduced by proportional control action, and it stabilizes the gain of the controller. Okay, so these are the advantages of a proportional. So where there is this, if you see this PID, where there is any disadvantage related to D controller, it is removed by I controller, and where there is a disadvantage due to I controller, that is reduced by D controller. So they are complementing each other. So that's why we are getting a better options, and proportional is again there for its outstanding advantages that we have seen earlier. Okay, so I think this much is today. This much is sufficient for today's lecture, and we will stop here. Okay, so most of the part from this unit is now covered. Okay, so let's meet in the next lecture. Thank you.